Welcome, everyone. Thank you for joining us today. My name is Sakshi Sethi. I'm with the Optical Society. I manage OSA's corporate membership program, also known as OIDA. We are really excited to introduce today's webinar. It's sponsored by one of our corporate members, Optiwave. But before we get started, I'm just going to take a minute to review a couple of housekeeping items. I'm sure most of you are pretty familiar with virtual content over the last year and a half, but just a friendly reminder for those of you who haven't used Zoom as much. If you need any assistance during the webinar today, there is a chat icon. It's located at the bottom of your screen. Feel free to send me a message there directly. There is a second button located next to the chat icon that says Q&A. This will be your big resource today, as you'll be able to post questions directly to the speaker so that he can answer them to you at the end of the presentation. So I recommend making sure you type in any questions that you have. It's meant to be a conversation, a discussion. Towards the end of the presentation, we'll have plenty of time to get through all of the questions. And then the final reminder is that today's webinar is being recorded. It's going to be posted on demand by the end of this week, early next week. So you'll be able to get a link for that in your email after the webinar. I'll also drop it in the chat box here shortly. But like I said, the recording will be available in a few days. So in case you're able to stay today and you think this was helpful and you want to pass it on to a colleague, they can watch it later. Or in case you have a different commitment at the end of the webinar, you can't stay through the very end, you can certainly rewatch it online at a later time. So that's everything that I have. I'm going to go ahead and stop sharing my screen and pass things over to our speaker today, Ahmed Atiye, to go ahead and get started.
Okay, perfect. Thank you, Sakshi. Hello, everyone, and welcome to this webinar. Let me share the screen. And then here you go. Okay. So hello, everyone, and today's webinar is about multi-core, single mode, and multi-mode fibers with trenches and air hole assisted design. My name is Ahmed Atiya, and okay, so let me go with the pointer here. Okay. Now, in today's webinar, I'm going to talk, provide some information, general information about Optiwave. Then I'm going to talk about mainly Optisystem features. Then describe the space division multiplexing for optical communication. I'm going to talk about multi-core fibers, single mode multi-core fibers and multi-mode multi-core fibers. And then I'm going to describe the analytical models in Optisystem used for single mode multi-core designs. Then I'm going to talk about the new component we introduced, which is called Universal Multi-Core Fiber Component. And then I'm going to show some examples and talk about how to incorporate the crosstalk calculations for the multi-core fibers into the Optisystem transmission system models, and then show small live demonstration, and then open for question and answers. Okay, so the first thing here is about Optiwave. Optiwave established in 1994, and it's located in Ottawa, Ontario. Optiwave offers different software packages which can be used for designing, optimization, and simulation of different components, links, systems, and networks. Optiwave, through these packages, can provide a very good advantage and distinctive competitive advantage through shortening the product time into the market, improving the product quality, as well as enhancing the productivity and cost effectiveness of the end product. Optiwave has licensed the different packages of their products in over than 1,000 industry-leading corporates in universities, research, and governmental institutions in over than 80 countries. Okay, and then let me move this one here also. Okay. Optiwave main product is can be categorized into 3 categories. One of them is the system level software packages, which include Optisystem, which mainly today will be concentrating on it. And then OptiSpice, which is an optoelectronic software, can be used for designing photonic integrated circuits and different optoelectronics components. There is component level software packages, which is including OptiBPM, OptiFiber, OptiGrating, OptiFDDT, and OptiMode. OptiMode is also going to be used with Optisystem to create the simulation for the multicore, multimode, and single mode fibers. And then the last package is on OptiInstrument software, which is a new software package. It enables users to communicate and control instruments remotely or co-location with the software. Now, users can download the different packages of Optiwave through the website. If you go to Optiwave website and then you go downloads and then click on the 30 days evaluation, then the forum registration page pop up, and then you need to create your own username, password. Once it's done, you can log on, and then you can have access to all software packages I've mentioned earlier. And then you can download them into the program files, Optiwave software. And then, as you can see here, this is the different packages of Optiwave software which you can download. Now, once you click on one of these packages, you're going to see different subdirectories, which includes the drivers, the documentation, and instructions, README files, and so on. Now, the main purpose of this webinar is, again, is an Optisystem software. So once you download the software, one thing which you can download as well is Optisystem samples. And this is a very good resource, actually, for users to be able to use for guidance, for information about the different applications. So if you go into the software and click on any of these directories, you're going to see subfolders in them, and then examples, many examples to describe the applications of Optisystem software, which I'm going to summarize here in different bullets here. The first one is advanced modulation, and you can basically support any type of modulation available in the market, from regular not return to zero, return to zero, all this kind of format and modulations, plus the advanced modulation through quadrature amplitude modulation, any format from 4 QAM up to 256 QAM. Pulse amplitude modulation, you can do 4 BAM, any type of BAM, even arbitrary BAMs like BAM 3, BAM 5, BAM 7, and so on, or user-defined BAM as well. Now, other application also you can address in Optisystem is the new 5 radio frontal, which is like addressing 5G applications and so on. So you can have many components in Optisystem to design your system to address the new radio applications. Optical amplifiers, also there is, as you can see here, one of the directories is optical amplifiers, where you have different designs. You can design erbium doped fire amplifiers, semiconductor amplifiers, Raman amplifiers. If you wanted to design any parametric amplifiers, you have the ability to do that. And also this software also enable users to do optimization. So if you want to do, let's say, for example, optimizing the length and so on, you can do as, or the BAM power and so on, you can have optimization. There's different algorithms to be used for optimization. Optisystem can be used for microwave photonics. It can be used for sensor applications. There is components for OTDR, Phi OTDR, FPG sensors. You can use incorporation with OptiMode. You can design photonic crystal fibers for biosensing. We did a webinar here actually on it. And then if you can go to resources of Optiwave, you can take a look at that. Also, Optisystem can address wireless communication, optical wireless communication for Li-Fi application, visible light communication, satellite communication. So all of that can be done through Optisystem. And mainly today, I'm going to concentrate on the spatial division multiplexing, where we're going to talk about few modes, multi-mode fiber. Actually, this is something which you can do in multi-mode fiber. There is a directory for these components, and then single mode and multi-mode multicore fibers. Now, Optisystem has over than 540 components, and these components are categorized in directories where you can click on them and then use them. And this component can be summarized in here in a couple of slides. The first one is like I'm talking about the sources. You have different CW lasers, LEDs, VCSELs, DFB models, Fabry Bureau, white light sources. Modulators, you have lots of types of modulators. You can have analytical models for Mach-Zehnder modulators. You can have single drive, dual drive, or single port, dual port Mach-Zehnder modulators. Electro-absorption modulators, you have as well phase modulators, amplitude modulators, as well as frequency modulators. Bit sequences, we have components which is pseudo-random bit sequences or user-defined sequences or compliance test patterns as well. Optical fibers, we have single mode fibers, multimode fibers, multicore fibers, which is mainly today's webinar about. And then also we have electrical modulators, which can support OFDM, quadrature modulators. Modulation formats, you have all types of formats, return to zero, carrier suppress, return to zero, dual binary. You can support differential phase shift keying, any type of MPSK, quadrature as mentioned, pulse position modulation, optoelectronics components. With the help of OptiSpice, you can integrate components like ring resonators and optoelectronics components within Optisystem to work, plus laser drivers. As you can see, there is different switches in Optisystem library, component library. Signal processing, we have a DSP, very powerful DSP components, equalizers, electronics equalizers, optical electrolysers, regenerators, 1R, 3R, 2Rs. It depends on what type of regeneration you wanted to do. FIC and bit mapping, there is different types here. Detectors, we have our models for the pen detectors, APD. Optical amplifiers, as I mentioned, all types of doped materials is available to do designs, or you have blocks of amplifiers as well. You can do optimization, as I mentioned, for gain flattening filter. We have waveguide as well as models for amplifiers. Electrical amplifiers, there is transimpedance amplifiers, limiting amplifiers, and automatic gain control amplifiers. Passive components, any component you can think of it in optical domain, you would have it available in Optisystem, from multiplexers, from couplers, arrayed waveguides, switches, attenuators, circulators, polarization controllers, and so on. Multimode components, you have the fiber, which is multimode fiber, multimode amplifiers, you have mode generators, you can work with linear polarized, LG modes, what type of the modes you are interested in. There is passive multimode components and special visualizers. Optical channels, as we saw, like we have fibers to support the physical channel or space wireless channels like Li-Fi, satellite, and free space optics. Visualizers, Optisystem has a huge library of visualizers and equipments. You can see optical signals with it, electrical signals, binaries, MREs. There is test equipment as well as we have added up, and this is coming up in the new release, Opti instrument component, where you can communicate with instruments and get data from instruments and use it in Optisystem. The components, most of the components can support bidirectional components, so you can go from east to west or west to east in your transmission systems. Okay, now I'm going to start with talking about this after this introduction about the spatial division multiplexing. And as you can see, this plot here is taken from this reference. And there's two lines here, as I can see. One of them is the commercialization progress, and the other one is the research progress for the system capacity versus the year, as you can see. And initially, between the 80s and late 80s, early 90s, you have the electrical domain division multiplexing can go up to these rates. And then when the optical amplifiers being erbium doped fiber amplifiers being developed and WDM systems start to increase the capacity. As you can see here, we move towards more and more channels. You have 40 DWDM channels. Channel spacing has been controlled. And with this is like you have different degrees of increasing the channel capacity through either the number of channels, the wavelength channels, or through polarization multiplexing, and using also digital coherent with the QAM and digital coherent systems. This capacity has been pushed towards, like as you can see here, towards 2020 and reach the capacity limit. And then beyond that, how to increase the capacity is to use the multiplexing, special multiplexing through either a few modes where you have over single core multi-mode fiber, or you can use multi-core single mode or multi-mode fibers to carry more channels. And then with that you can increase the capacity drastically. Now in this this chart here, just to show you how is the capacity scaling. As you can see, this channel capacity is log 2, 1 plus signal to noise ratio times 2 times the number of wavelengths here. But if you add up the parameter for a spatial path, you can increase the capacity drastically. Okay, now in Opti fiber, we can have a multi-mode fiber, and then this with single core, you can have few modes, and if each mode you can carry different data rates on it and increase the capacity with this way. Or you can have multi-core fibers, and with the multi-core fibers, either each core has a single mode or multi-mode, and with that also you can do increase the capacity. Now, what you need to worry about here is to design the core in terms of the refractive index profiles. You can have step index or graded index, and also you can add up features like trenches and air hole assisted to control the crosstalk between the modes in a same core on a different core. And now, if you can see here, this is a kind of 70 cores structure and taken from this reference. And if you zoom on this structure, you can see these two different cores neighboring between them, the gap G, and then also here you have all holes. And then as you can see here, there is the refractive index profile for this core and for this core are not equal. That's why we call them heterogeneous. And then you have a trench, and then the air holes also of that will help the control of the crosstalk. In the Optisystem, we have currently in release, which is up to 18.0 right now, you have the analytical models, which is you have different components like multi-core fiber component, where you can calculate the crosstalks between the different modes. And you can also have another component which is used for calculating the effect of bending radius on the crosstalk, and then the another component which can calculate the effect of core pitch between the cores on the crosstalk. Now, in the next release, which is coming up sometime in September, is early October, we're going to have the new component, which is called Universal Multi-Core Fiber. Now, this component is going to be able to communicate with OptiMode, so you can do design of your structure in OptiMode, generates your mode profiles, and then effective refractive index, and then import them into Optisystem, and then calculate the crosstalk. And after calculating the crosstalk, I'm going to show you later on how to take the crosstalk and do the calculation of the effect of crosstalk on the transmitted signals. Now, in this here, give more details now about the analytical models in Optisystem for the multi-core fiber. This is the structure of the multi-core. You can have core 1 and core 2, and then you have trenches. You can have this is the parameters for the radius of the core 2, and then this is also controlling this parameter, the trench width, and so on. As I mentioned, this is the components uses analytical models. The other component, the universal multi-core component, which is I'm gonna today demonstrate it using CPP component, which is a component we have in Optisystem as a development environment. So I'm going to demonstrate it today using the CPP component, and then eventually again it's going to be a new component. It can be used as other components in the release coming up in September-October timeframe. So in this component here, you can control the number of cores. You can control as I mentioned, the bending radius. You can control the core pitch between the different cores. This is a general description of the refractive index profile. You can control the refractive index profile as you see, and then you can control the different parameters for the cores. And then you can simulate almost every possible configuration. So you can have homogeneous with no trench. So you can have core 1 and core 2 have the same refractive index profile, no trenches in the design. You can have homogeneous with trenches assistant, and you can have also heterogeneous with no trenches, heterogeneous with trench assisted, homogeneous one core with trench and the other core no trench. You can have heterogeneous one core with trench and the other core with no trench. So the idea here is the flexibility in these components in Optisystem, which uses analytical models again to calculate the coupling coefficients and the crosstalk. I'm going to show it to you in a few minutes. It's very powerful to do all the kind of simulation you need. However, if you wanted to look into multi-mode applications and then you wanted to design your own structure, then you can use again OptiMode to design the structure, calculate the field profiles, calculate the effective refractive index, and then load that into Optisystem and then do the calculation of the system for crosstalk. Okay, so the calculation of the crosstalk is based on, anyway, is we can use the coupled power theory and to calculate the crosstalk, and the expression, as you see, it's analytical expression using these coupled equations, and the power for core P as function of the distance is given by this formula where HPQ is the coupling coefficient between the core P and the core Q. Now, in the component in Optisystem, once you double click on the component, you're going to get the pop-up, which is the properties window. And then in it, you can enter, as you can see here, the parameters, the different parameters, the number of cores, the bending radius, and so on. If you need any help on how to set up the parameters, you can click on the help button and you're going to get access to the data sheet of the component. As you can see here, just the depictive illustration of how is the coupling. So the light is going through, for example, core 1 here. Some of it is going to couple to core 2, which is core G. And then you're going to calculate the cross coupling between the two, the crosstalk between the two cores. Now, in the component, which is the multi-core fiber component, as you can see here, you have an outcome of the calculation where you can see the coupling, the crosstalk between the different cores. So for example, this is between core 1 and core 2 and core 2 and core 1, and this is core 3 and core 1 and core 3 and core 1 and so on. So you can have all the crosstalk parameters calculated and offered to the user. And this is the total crosstalk for, let's say, core 1 and core 2 and core 3. In this chart here, just show you for example, the component which does the effect of bending radius. So you can sweep the bending radius, and then you're going to get the crosstalk at the effect as function of the bending radius. And the third component, which allows you, after you design the parameters for the fiber, the multi-core fiber, then you can see the effect of core pitch when you sweep it. And the crosstalk as function of the swept crosstalk. So this is the three components which is currently available on Optisystem, and you can do design with them in single mode multi-core fiber. Now we noticed that there is lots of people using these models for multi-mode fibers, which is, we think it's not correct because the effect is not correct. So what we did is actually we allowed the user to use OptiMode software to design the structure with it, and then calculate the field profiles, and then calculate the effective refractive index, and then load them, as I'm going to show it today to you in the live demonstration. So this is a kind of introduction about the new component. Again, the simulation is done today with the CPP component, which is a component. You can find it in Optisystem libraries, component libraries. And then the universal component eventually is going to be a standalone component in Optisystem, where you can use OptiMode again to design the structure and then calculate the mold field profiles, and then get the effective refractive index profile for each mode, and then in different cores and load them. Now, the process of designing the multi-core fiber, we did a webinar on it a few months ago, and you can find this webinar at Multicore Fiber Designs and Analysis at our website here, optiwave.com. Okay. Now, the next step is after you calculate the crosstalk between the modes in the different cores on the same core, then what you need to do is you need to do the simulation to check how the system would be affected by the transmission of the signals in the system level. Okay. Now, this is the look of the CPP component. It's C++ component, and in it you can add up parameters. As you can see here, we create all the parameters required to allow the calculations, and you can load the files, the field profiles and the index profiles into the component. And then with that, you will be able to simulate the crosstalk in Optisystem. The data sheet is here. You can see the different parameter of every parameter and the ranges and the units and so on. Okay, now here in this example, just to show you, and this is what I'm going to demonstrate today, is the structure which has a 21 heterogeneous multimode, multicore, and square lattice. So you can see the lattice here structure is a square, and there is 21 cores here, and you have core 1 and so on. And this is taken from a reference published in 2017. And here you can calculate the total crosstalk as function of the core pitch. And this is what we're going to demonstrate today in the live demonstration. Now, the crosstalk Optisystem will allow you to calculate the intercrosstalk between the selected set of core and mode pairs, as well as the total crosstalk. Now, the example, it has a structure, as you can see here. The core is a graded index profile with alpha profile, and then you have the radius of the core, the radius of which defines the width of the trench, and then the other parameter R here, which defines the distance between the core and cladding. And then this is the different parameters, the refractive index, relative refractive index parameter, and then for all these parameters taken from the reference. This design allows 4 modes to propagate. This is LB01, LB11, LB21, and LB02. Now, the crosstalk is calculated as function of the core pitch, as I mentioned in the earlier plot or graph, and at a specific bending radius of 140 millimeter. In this component, you should be able to also sweep the bending radius if you want it. So you have capability to do a sweeping of the core pitch. You can sweep the bending radius, and then you control, as well as you can see here, the length of the propagation length. In this chart here, just to show you the LB modes, which is for that fiber, you have 4 modes here, mode 1, 2, 3, and 4. And this is the structure of the modes, the intensity of each mode. And these modes, again, is going to be designed in OptiMode software. So you use OptiMode to design the structure, which is, as I showed you in the previous slides, it's a 2-core with a trench, and it's very simple design. And then this is supports 4 modes, and this is the different modes. This is mode 3, and this is the 4th mode, which is gonna be LB21 here, as you can see. All of this information is available in OptiMode. As I mentioned, you can go to the webinar on Optiwave website, and then you go through the process how to go to design and then operate the OptiMode software. Okay, so the example here we created in the CPP component 4 examples. I remember correctly, 3 or 4 examples. Our team has created these examples, and based on published work, which this work selected to be either like some of the work you're going to see that it's include only theoretical calculation or include also experimental calculation. So that's give a kind of confidence about the models has been and the calculation has been used. Okay, so now if you double click on the component, I'm going to show it to you. You're going to have access to the component properties. Now in this window here, you're going to see that this is the project browser. You can see the graphs generated for Crosstalk and also the outcome of the calculation. Now the instruction how to use OptiMode and how to use Optisystem is described in the information here as well. Now all of this information would be easier once we have implemented it in the next release as a component in Optisystem. Okay, let me just, I think it's one more slide here. Okay, this is the result of the calculation, which I'm going to show it to you in the demo and compare it with the published paper. Now, Optisystem, this right now software can give you also the file, a text file, which also describes the crosstalk for all the cases here, because we swept the core pitch in a range between here 35 and 45 and in 21 steps. So you're going to give all this every step what would be the crosstalk between the modes. And this is the published paper reference, and this is what is we got from Optisystem, and you can see that there is a very good agreement between the two simulations. Okay, now the other part which very important in this simulation process is to study the effect of the crosstalk parameter. So you did the design of the multicore fiber, you looked at the crosstalk, and then what's the value of that? The value of that is to implement it in a system using the modulation scheme which you are interested in, and then do the transmission and look at your system performance. And that's what this example enables you. So the example allows you to do different processes. The crosstalk is controlled through this attenuator here. So you allow the modulated signal to couple into the transmitted signal, which is interest signal here. And the coupling depends on the attenuation again, which is the crosstalk parameters. And you can control either one of these scenarios. You can have modes are the same at the same wavelength in different cores, or you can have modes, let's say, at different wavelengths in same core, or you have modes at the same wavelength in different cores. So all of these different possibilities can be simulated using this kind of implementation. And this is the implementation I'm going to demonstrate it to you shortly. It shows all the components. Right now, I'm using here non-return to zero, very simple scheme, and shows you the way how to set up the configuration. Okay, so now we're going to move into the live demo. And it includes, as I said, is the multicore fiber component using the CPP component at this moment, and the crosstalk consideration and Optisystem. So if I move into the Optisystem software, okay. So this is the one of the examples. So if you go to this example here, let me see here. So in this, we created these three examples here, which is based on air hole assisted, and then in the air hole assisted, there is two examples, one of them 30 cores. And this is the files which you need to run in OptiMode at this moment, okay? And then this is as you can see, this is the reference which is used to verify the models and the results. And all of these results has been verified as you see. Now, in terms of the component, as you can see here, if you double click, this component is a development environment, which is something we like users to use for if they wanted to develop their own codes, and then eventually they create the drivers. As you see here in the every components, there is a driver. So let me see back here into, this is the demonstration example. This is the driver, which is created from this component and has to be loaded with the component. So if you go to the component here, double click on it, you can see this is load the CPP driver, and this has to be loaded. You have to put the driver in the same directory, or you have to put the path of it. So once you load the driver, You can set up the other parameters, like for example, fiber length here, 100, number of cores, 2, and this is the core parameter files, and this is you load them from the OptiMode results. And as you can see here, in this directory here again, in this example, these are the files where you have your design in OptiMode. You design the structure, you design the SQL, and then you calculate the using the, for example, the LB solver here. And then once you calculate, you load the field profiles, as you can see here, into Optisystem Components. So you take the path here, and then you load the files. So you load the files which you need, and then once you load the files, basically for the effective refractive index, the field profiles, and then you can set up here the pitch minimum values and so on. You have a capability to do sweeping of the core pitch, or you can sweep also the bending, and all of this is being, again, if I'm going to show you here the component. This is the new component which we are working on. It is going to be a standalone component located in the like in default optical fiber library. And in it, you can see, you can set up all these parameters in a standard way. So this is something, again, is going to come up in September, October time frame in the next release. Now, once you enter these files, the instructions how to operate all these files and to create the files, the field profiles and the index profiles, you load them, and then you do the calculation. Once you do the calculation, the files will be loaded into Optisystem, and then after the calculation being done, what's happened is the graphs is going to be generated here. The calculation is finished, and then you have the graph here. Shows you the graph. These graphs, you can download them as exactly similar to any graph in Optisystem. And then this is also the file where it tells you if you have any errors or type of errors and so on in the calculation. Now, if you go into the text file, one of these text files here, I have to see it properly actually. You can see this is OptiMode results, and this is the crosstalk. And this is the file where you have all the crosstalk, every step. When you again, is we have the core pitch here is swept between 35 micrometers to 45 micrometers, and then every step here you have see the crosstalk between this mode 2 and core 2 and to mode 2 and core 1 and so on. So you can define the crosstalk, which parameter, which modes you mode pair in which cores you wanted to do the calculation, okay, on it. So this example is, again, we have 4 examples. In this is another example, and this is the reference of it. It's also you can also look at it. This is the profile, and this is the paper, and we able to generate exactly the same curves in this design. So this is something which is you can use as guidance for your specific designs. Okay, so this is one thing. The other thing which I wanted to demonstrate to you is the transmission. So the transmission, which is I mentioned to you here, you build your own system. The way, as again here you have the default components and the libraries, and in the components you can select the components required from transmitters. All these components, the 500. If you don't know the component, you just try to click in this area and find component. You can search for it and then find the proper component. Now this system is built here, as you can see, with two lasers. This laser is, as you can see here, it's scripted the information as start, and this one here is scripted as start plus a shift, which is based on separation. And these 2 parameters are scripted added up in the global parameter here, as you see. And one of them is the separation 100 gigahertz, and the start is 193.3. So which means you can select the wavelength of operation in the global parameter here, and then you can set up your separation. So if you wanted to do the crosstalk simulation here between the same wavelength in different between, let's say, different modes at the same wavelength, then you can put these two the same wavelength. If you have different cores at different wavelengths, you can select also the wavelength separation, and you can set up the proper wavelengths. And then again, here in the attenuator, you can set up the attenuation. Here in this example, what I did is just only the sweep between them, just only to demonstrate the effect. And then eventually you can set up the fiber based on your system and look at the bit error rate here, or look at whatever depends on the modulation scheme. You can look at this, but the core design is this block here, basically, where you create the effect of crosstalk into the system. So once you run this system here, it's going to take some time, but eventually I didn't run it ahead of time, honestly, but we can run it right now and maybe start the QA. And then, as you can see here, it's going to go through the iteration one by one. And once it's done, you can look at the progress here. And then eventually we can look at the effect of crosstalk at the performance. Okay. So let me move on into the back again here, just to show you. This is one of the handouts. Also, we wrote about air hole assisted multicore fiber. And we described the whole process, the application, the comparison with this. This is the design using the OptiMode, and the comparison with these published papers. As you can see here, this is one of the good resources. The webinar on Optisystem website is also another good resource, which you can take a look at it for future applications. Okay, so now with this, I'm gonna pause and then open for a Q&A. Thank you very much for listening. So let me see here.
Ahmed, before you start the Q&A, I just wanted to mention there's one question. If you look at it in the answered tab,
okay,
it moved there by mistake. If you could start with that one and then move to the open questions.
Okay. Okay, so this question says, does Optisystem have holographic beam splitter, or what component can I use in Optisystem as a hologram? Okay, so this component, like holograms, we don't have a specific component called hologram component. So I need to think about it honestly a bit more to be able to answer your question. If you could give me an email at my email here, ahmed.atiyah@optiwave.com, and then we can discuss your application in more details and hopefully help you, because it could be used with other software in my mind right now, but we can talk about it later on. Okay. Okay, let's see the other questions. So here question, it says, let's see, just following up. Is your crosstalk calculation, okay, I'm actually, okay, is your crosstalk calculation only for co-propagating, right? How about counter-propagating? So at this moment, yes, the calculation is unidirectional. However, you can do is you can duplicate the setup and then assume that the signal which is coming in backward can calculate the crosstalk. So we don't model counter-propagating crosstalk because the fiber, we assume it's unidirectional at this moment. Okay, so another question here says, thank you for the presentation. Is it possible to import mode field and effective index profiles from another source than OptiMode? Yeah, I mean, in principle, as long as you can keep the data structure the same way, then should be no worries in my mind, yes. Another question, can I simulate evanescent field and FPGs? So you can simulate FPGs in Optisystem. There is a component to do that. And if you wanted to look at the field propagation, like a BBM or something, you can look at the fields there as well. So you need another software to use it. Now the Optisystem can talk to OptiBBM, and you can load files into it from there. So it depends on the application which you are interested in it. You can do that. Okay. So one question here is, I have to hold this here. Okay. I'm interested to design a symmetric Mach-Zehnder modulator with taper. So how we can design and simulate it by Optisystem. So the design of Mach-Zehnder itself, you can design it in other software, and then you can incorporate its parameters in Optisystem software. So Optisystem software, the parameters of the components can be used based on the structure design which you did. So in terms of the transfer function of these components, you can load your own transfer functions, like for example, and you can use it in Optisystem. Is it possible to create ring core profile using Optisystem or OptiMode? You can use it on OptiMode. Definitely, you can design your own structure, whatever structure you have in mind. You can do it, and then once you design it and do the propagation, you can load the field profiles and effective index into Optisystem, and then you do the crosstalk calculation. So the flexibility. That's the beauty of this new component, the universal multicore fiber component, is it allows you to design whatever structure you have in mind, actually, and that would enable you to study the performance of crosstalk, and then eventually the effect of this crosstalk and the transmitted signal. So that's the flexibility which we incorporated in this kind of new components, is the possibility to design whatever structure you have in terms of refractive index profile, of structure of the core, as well as the if you want to add up with air holes or whatever the material you wanted to add up. The question here, it's is it possible to apply random orientation of the bending when calculating bending induced crosstalk in the multicore fiber? So orientation of the bending, so the bending is calculated if I understand the question in one orientation, because the propagation is in the Z direction, and there is no other influences beyond on the propagated signals in other directions in the calculations. So if you can explain more on this question, you might send me in the email, and then we can try to discuss this also with our team who have better experience on the OptiMode software. Okay. Can I model photocrystal ring resonators on Optisystem? The design of this component and structures can be done in OptiMode or OptiFDDT or OptiBBM, like the structures, the modes, the fields is calculated external of Optisystem. Optisystem takes the field, the effective refractive index, and calculate the crosstalk. So this is the process of doing it. So it's a two-step process. One step is to use other software to create the design the structure, calculate the field profiles and effective refractive index, and then eventually take calculate the crosstalk. Okay, another question here is how Optiwave is used for different orientation in multimode LB11, LB1B. Okay, so it's the designs is done in OptiMode, and OptiMode handles these types of modes. Okay. Okay, another question here. There is a request here if we can do a webinar on integration or co-simulation of Matlab with Optisystem. So this is something we can do that. I think if you go to Optiwave resources, there is a webinar on it already, but we can incorporate maybe a new one with more details on new applications to do that. Okay, another question here is how to realize practical mode multiplexing in Optisystem. Okay, so Optisystem, the mode multiplexing right now is done through a component which it assumes that the modes are coupled properly and there is no crosstalk between them or anything like that. So you cannot control the field profiles of these modes. However, you can design the multiplexers in other software and then use their parameters maybe in an Optisystem. So this is something which we could talk about it if you like in a separate email. Okay, another question here. Which is better software to design optical amplifiers, Optisystem or OptiBBM? Actually, we want to use different types of elements for their operating wavelength. Okay, so Optisystem is the software used for designing optical amplifiers. It has the components, all the basic components to build an optical amplifier, from the fiber itself, the doped fiber, the bumps, the multiplexers, and the isolators and everything else. So all these components are available in Optisystem component library, and then you can use practical parameters in them and then use them to build amplifiers. And the models in the optical amplifiers has been verified experimentally many times. Okay, so another question is, did you validate the models of Optisystem for the new multi-core fiber component? Yeah, we did actually in all these papers which I mentioned in the discussion today has been some of them is theoretical comparison with like the published papers have theoretical models, or some of them have experimental and theoretical models. So the verification is basically done based on two types of published papers, which either theoretical and experimental, and that give the kind of confidence about the models used and the system component. Okay, is it possible to do a structured design for optical nanofibers by taking into account the vector aspects of the propagation of optical fields? Now, nano designs can be designed in OptiFDDT, and that's something which is also can be done in another software, and then you can look at OptiFDDT at Optiwave's website. There is webinars talking about that. Okay. So another question here, what's the difference between the new universal multi-core fiber component and the other component in Optisystem, other components in Optisystem? So the universal multi-core fiber component, the universal component, it allows the user to design any structure and it starts for multimode as well as single mode. However, the models, which is we noticed that in most published papers, they use single mode analytical models to model the multimode multi-core fibers, which is I think it's not right. So this component, the new component, allows the user to look at actual fields in these multimode structures and then calculate the coupling coefficients and the crosstalk in actual life. And that's where, when we compare to experiments, the models were very accurate. Okay. Question here is, how can I design different rare air co-doped waveguide amplifiers? Here only, okay. So in Optisystem right now, we allow terbium doped waveguide. However, we can give you access to maybe to load different types of emission and absorption structure, but we have to control the operating wavelength ranges and all these things to allow the models, and we have to double check the models about the because of absorption and excited states and all these things has to be taken into account. So this is something we can work on it to address it. Okay. Is there any component available on quantum dot semiconductor amplifiers? Yeah, it's actually something, this is coming up. We are working on it, and This is we are introducing quantum dot semiconductor optical amplifiers as well as quantum dot lasers. So this is something looking forward to introduce in Optisystem. We are working on the models currently. What else? Okay. Do I need to acquire OptiMode to be able to use the universal multi-core fiber component? I think this is a fair question, because to be able to use the universal multi-core fiber component is you need to be able to load the field profiles and the effective index profiles, and this is you need to create them. So one of the questions today was, can I load it from anywhere else? Yes, you can load it from anywhere else as long as you have the structure correctly. So if you have another software to generate these mode field files, that's fine. Else, you need to acquire the OptiMode software, definitely. Another question, is it possible to use current multi-core fiber component multi-mode? As I mentioned, it's the multi-mode models, some users or some published papers actually using the analytical models for multi-mode multi-core fibers, which is not right. So the best scenario is to use the new component to be able to address the multi-mode multi-core fiber applications. Okay, can I design heterogeneous trench air-assisted multi-core multi-mode multi-core fiber? Yeah, definitely. As I mentioned, there is about 7 possibilities to use. And this is actually for multi-mode. Yeah, for multi-mode is you can do any design you wanted. As I mentioned, you can do trenches, no trenches, with air assisted, with no air assisted, heterogeneous, homogeneous, all possible structures. You can do them in OptiMode and then load them into Optisystem, new component. Yes. I think this is the last question. I'm not sure if there is any other question. Okay, there is. Do you have OFDM with MF good reference paper? Okay, so yeah, please send me an email on my email here as you see it on the screen, and I'll forward to you some papers on it, definitely. Okay. I think it's that's all. So I think we can conclude. Thanks very much everyone for listening and for the questions. If you have any question, you can send me an email to as you see here at ahmed.atiyah@optiwave.com, and I'll try my best to help and support you in your requirements and needs. Thank you very much.
Thanks, Ahmed, and thank you all for attending today's webinar. We had over 20 fantastic questions, and I know you were going through those quite quickly at the end, but if you have any further questions, the best way to reach Ahmed is via the email that was up on the screen. I did send this reminder to everyone at the start of the webinar, but in case you did join late, today's webinar was recorded, so you will be able to access the link to view the video by the end of the week. I am dropping that text now in the chat box for everyone. So if you click on that link, I would say by Friday, Monday at the latest next week, you will be able to access the recording from today's webinar and catch any of the content that you missed. Again, I appreciate Optiwave for sponsoring today, and thank you all for attending, and I'll see you guys at the next webinar.
Thank you, Sakshi. Bye-bye.
Thank you.